So did you download the software?
Yeah, we have downloaded Xilinx.
Okay, fine. So before going to take that Verilog, so I will just go through the basics of digital design. Okay,
Okay.
so as you know, and the main difference between analog and digital signals are
Main difference between analog and digital signal.
yeah,
Yeah, like digital design is like on the logic of 0 and 1,
yeah.
and then the analog is like with a varying with an x and y axis.
Uh, so fine. The main what is the necessity of that digital signal? So we are in a real-time environment. We are having all the signals are in analog in nature.
Yeah.
But what is the necessity of digital signal in that case?
To understand to the computer,
To get to the logic level 0 and 1.
Yeah, I'm asking the necessity.
to understand to the computer level,
Okay, for only
so the
that purpose.
can't take like a system can't take an analog signal, right?
The system can't take. Okay. Actually, the processing inside the computer is purely in form of binary.
Okay,
Binary.
yeah.
Yeah. So actually, what we are doing means if I'm taking the analog signal and if I'm taking that signal into processing, then it will take much amount of time as well as memory because I have to sample every individual samples. Then only it is possible
Oh,
to analyze the entire signal.
Okay.
So in the case of a digital signal, if I want to process the signal, I have to quantize that output. And
Mm-hmm.
from the analog signal, I am using the ADC, that means analog to digital converter, and I am converting the signal into some form of discrete and digital signals. Then afterwards, what I am
Mm-hmm.
doing means inside the DSP processor, because DSP processors are made up of only the digital processors. So the processing is very much simple, and I'm able to store my signal, and there's no need of much capacity is necessary for storing the entire signal. So that's why we are
Mm-hmm.
preferring the digital signal rather than analog signal for processing. So,
Okay.
but in case of analog signals, what we are doing means, for example, if I'm connecting any sensors or actuators, then directly I will get from the signal, and I have to sample the every output. Means it is complicated for me. Just a minute, sir.
Mm-hmm.
Hello. Good morning, sir. Sir, the class is started, sir. Yeah. Yes, sir. We are going actually. The class is going on. They joined. Yeah. Hello.
Yeah, hello.
Yeah. This is what we are preferring the digital signal.
Okay.
So because the processing of analog signal is complicated and complex process. So that's why we are
Mm-hmm.
preferring the digital signal for processing. And our input devices are from either from any sensors, actuators. So these are all kind of input devices. It sends a signal. Then afterwards, what we are doing is we are converting into digital in the form of using devices like analog to digital converter. Then afterwards, we are converting the signal into digital. Then we are processing that signal. So afterwards, we are converting the same processed signal into analog form. Then we are setting into the output devices. So this is the way we are doing the digital processing.
Digital.
Yeah.
Yeah.
This is why we are preferring the digital signal rather than the analog signals, because the main thing is the memory requirement is very much less compared to the analog signal. Then the next purpose is the processing capability is much high for digital than the analog signal. And for
Mm.
digital processing, the main problem is because we are quantizing the signal, sample and quantizing
Mm-hmm.
signal. So there's some error will occur because how many samples we are taking, in that way only we are getting our accuracy.
Mm-hmm.
So if you are processing that signal into digital, so that little bit error, which is also not a much compared to our normal analog signal. So if you are carefully taking our samples, it is easy to reduce the error rate. So before going to the Verilog, let me just thorough about digital design. So these things are we already aware about the digital circuits, the logic gate, then what is the Boolean algebra, then K-map specification, then combinational and sequential circuits, then memory elements and integrator circuits. So these are all coming like in that order. So we know the logic gates are. Hello.
Yeah.
Yeah. What is a logic gate?
And or not nor
Mm.
and
NAND nor XOR. So these are all logic gates. So in our logic gate, we are having two types of gates. One is a basic gate, another one is a universal gates. So basic gate is
and
a
an or
and or
and or
then not. So these three gates are basic gates. Actually, and or not functionalities, which is made up of only the Boolean logic. Is if both the inputs are 0 means for AND gate, the output will be 0, and if any one of the input is 0 means the output will be 0, and if both the inputs are 1 only, then the output will become 1 for AND gate. And for OR logic,
any one input should be 1.
any one input should be 1 means the output will be 1.
Yeah.
if
For
Rest all 0.
both are the same.
yeah, if both the inputs are 0, then the output will be 0. So this is normal functionality and truth table and symbol of our normal logic gates. So
And we came across some other gates also, like match, make,
what gates?
match.
Match
Yeah,
gates.
it's like, yeah.
Okay. Actually, what is the functionality of that gate?
It's kind of XOR, but 0 and 1 is 1, but 1 and 0 is 0.
0 and 1 is 1 and 1 0 is 1. Okay. I didn't aware of that gate. May I refer and I will tell you on our next class.
Okay.
Okay, match gate. Well, it's
Yeah.
a new technique or something existing?
Actually, it's been working with the neuromorphic computing. They're using this match gates, like majority gate.
Oh, okay. Majority gates. Okay, fine.
Yeah.
Okay. Actually, that is a different form of CMOS. Instead of a CMOS logic, that's an alternate form of gate preparation.
Yeah.
That's a new technology. Actually, currently we are not having any real-time functionalities or fabrication for that technology.
Okay.
But for digital computing, we are using the for general normal gates are only these gates are considered. Our normal AND or not and XOR and XOR buffer. So AND or not are universal gate. Basic gates and NAND and NOR are our universal gates. Actually, NAND and NOR are universal gates one because from the NAND and NOR we are able to generate any functionalities. That's why these two gates are considered as universal gates. So these are all the truth table. I think you already know about that. So next one is the Boolean algebra. So in Boolean algebra, what is the functionality?
Boolean algebra. We didn't remember actually.
Okay, fine. Yeah, okay. Then I will say. So in Boolean algebra, what we are doing means because we are generating any other logic function means in terms of only the variables. So if I want to generate a truth table, then from that I will form the equation. So for that, For that expression, we are using the Boolean algebra. So, which is having some set of rules we already consider from the Boolean algebra. So, it is able to reduce the term, and that means we are simplifying the expression. So, if I am able to simplifying the expression, then alternatively, which means we are reducing the number of logic gates from the
Yeah.
minimization. So that's why we are considering the Boolean algebra to reduce the number of logic gates. So in that we are using the truth table. So truth table in the sense from the number of inputs we are generating our output. So based on the input, how the output will be generated. So that is the truth table. So from the truth table we are generating our expression. Then through Boolean algebra we are reducing that expression into some simplified form. So that form is called as a, that means simplified logical expression. So that is a, yeah, that is used to implement our digital logic circuits.
Okay.
So if you consider this logic, actually you are having three inputs x, y, z, and the output will be considered the f is it will be changed like that. So if I want to generate a equation, then we know you have to form the algebraic expression. So if I generate the function means x bar y bar into z, the which are the outputs are 1, so we have to consider that expressions alone. So here for f the value will be 1, then 4, then 5, then 6, then 7. So these values contains the output as 1. So if I consider the value, so the expressions will be like that: x bar y bar z plus x y bar z bar plus x y bar z x y z bar plus x y z. So this is a normal expression. So actually the 0 which indicates the complement of that value, and 1 which indicates the actual value of that output. So if it is under x it is 0 means that's a x bar, and if it is 1 means that actually the value that is x. So likewise you have to write our expression. So if I am simplifying that expression, then the output will be like that: x plus y bar is z. So for example, so x bar y bar is z plus first expression is x bar y bar is z, then next one is x plus y bar is z bar.
Yeah, we got this one. We know this.
Okay, that simplification you know now.
Yeah. Can you tell me if we come like x into x dash means 0, right?
X into x dash equal to 0.
0, yeah.
Yeah, x plus x bar equal to 1.
1, yeah.
Yeah. So that likewise you have to simplify the expression, and if it is having x plus y bar is z, then we are able to split the expression into x plus y bar into x plus z.
Yeah.
So likewise we are simplifying means you are getting the output like that. So that simplification you know now.
Yeah.
Okay, fine. Then I will continue the topic. So, and this is the basic identities of Boolean algebra. So, if you know this expression, then we are able to reduce our logic gate into simplified expression. So, by that we are reducing the number of logic levels of our digital circuit. So, next one is a De Morgan's theorem. So, what is the necessity of De Morgan's theorem?
Simplification of the Boolean function.
Boolean function. So, what it says actually?
What
Actually,
states?
simplify it by dividing the equation and combining it later.
Yes. So you are having two expressions x and y means, and the Boolean algebra states that x bar plus y bar is equal to x into y the whole bar, and x bar plus y bar is equal to x y the whole bar, and x bar into y bar is equal to x plus y the whole bar. So this is the actual two expressions. Okay. So by that we are able to generate our normal universal gates from the expressions. So that's why we are using the De Morgan's law to consider for changing our gates into any form. That means either into NAND or pure NOR implementation.
NOR.
Yeah. Then
Yeah, got it.
so this one is you know, I think. So from the expression we are simplifying that expression into some simplified form. So in that
Okay.
ABC plus ABC bar plus A bar C. So here you are having ABC AB as common. So AB into C plus C bar plus A bar C, and C plus C bar is 1. So AB into 1 equal to AB into 1 plus A bar C, and which is equal to AB plus A bar C. So like this we are simplifying, that means we are getting only, so here one AND gate, and here one AND gate, and here one NOT gate, plus here one OR gate. So simplification is total simplification is only 3 steps. So here you are simplified that expression into only the, it contains only 4 logic gates. So instead of I'm using the same expression, I'm getting more than 4 or 6 logic gates. So that's why we are considering the Boolean expression to Boolean algebra to simplify our normal expression. So next one is a complement. So complement mainly for considering the that means to generate the function into NAND or NOR. That means we are generating that function through the De Morgan's theorem, so that we are able to represent the normal logic gates into purely in the form of NAND or NOR logic. So that's why we are using the complement of a Boolean function. And so the problem using the Boolean algebra is, hello?
Time consuming?
Yeah, time consuming.
Yeah.
By what? Time consumption in the sense?
Building the equation like the big expression that complex function.
Yes, of course. So if the expression is a little bit different, if more than 4 or 5 variables, if we are considering, which contains a number of expressions, so it is complicated to solve that expression. So which is a tedious process for a Boolean algebra. So we are considering the alternate approach as a K-map, corner map approach to simplify our normal logical expression or truth table into simplified Boolean function. So K-map functionality, do you know?
Yeah, we know that.
So if it is having an output like that, so we are able to use the 2 variable K-map pins. We are having 4 boxes, and in that we are just applying our output here. So in that what we are doing is just the adjacent boxes are covered, so that the common variables are taken and considered for simplification, and if the variables are not common, just we are left that variable. By that we are simplifying that expression. So inside that we are having the min terms of that particular functionality. So likewise we are simplifying that expression. So here is a example of some form of K-map. So here you are having 3 variables. So 3 variables x, y, z, and the x variable is 0, 1, and here 0, 0, 0, 1, 1, 1, 1, 0. So this is in the form of gray code order. So because in our normal binary logic, what we are writing means 0, 0, 0, 1, 1, 0, 1, 1, likewise we are writing. But in the case of gray code order,
Yeah. Good.
In the form of a gray code, what we are doing means we are considering likewise. That means 0, 1, then after that one we are having 3, then only it comes to 2. So likewise we are writing. So and if I am writing this expression, the corresponding minterm will be 0, 1, then the output will be 0, 1, then 0, then 1, 0, 0, 0. So here there is no adjacent terms or ones. So maximum grouping only we have to see. So if all the 8 boxes are grouped, means we have to consider the maximum possible groups, but here there is no adjacent ones are there. So here all the elements are taken as an individual element.
Okay.
So by that the output will be comes like that. That means for this value and this value and this value. That means x bar y bar z plus x bar y z bar plus x y bar z bar, because there is no groupings are possible in here.
Okay.
And if I'm taking this condition in this table, here these two ones are grouped. So the output will be here. There is here only one term is common, that is v, and here you are having w x bar. So u into w into x bar is a expression, one expression, plus the another one will be you have to group these four elements. So for this one and this one, the common variable will be 0, that is v bar, and for this one and this one you are having the common variable is x. So the output will be x into v bar plus, and here you have to consider this group alone. So the output will be, the common variable is here is 0, so w bar, and here u into v bar. So w bar u v bar into w bar is the expression. So if we are adding the expressions, means the three element only comes under the output.
One. Yeah.
Not one. Actually, the expression will be simplified as only three functionalities.
Yeah.
So if you are seeing this, means here you are having adjacent one, so you have to group this element. So in that there is no common variable, because here 0 and here it is 1, so we are not taking this one, and here you are having one as a common, that is x, so the output will be x. So if I am doing the Boolean algebra, means I have to simplify the expression into two terms. That means the x is common, so x into y plus y bar, and y plus y bar is equal to 1, so the output will be x. So like I see here, simplifying that expression. So this is also one form of simplification. So here also what they are considering, means they are grouping this four elements, and here this is 4 and here this is 4. So maximum possibility is we have to consider all 16 combinations if all the boxes are contains 1, or else we have to consider 8 boxes if it is possible, means we have to group like that. So there is also no other possibilities there. So afterwards we are considering the 4 possibility. So here 4 boxes are grouped here. That means 4 elements are grouped here. So here it contains one variable. The output equation will be, and here we are also grouping these 4 variables, and here also we are grouping for these 4 variables. So likewise, if we are simplifying this, we are getting the expression like that. So here we are vw bar, and here u bar v bar, and here uw. That means if you are writing the expression, then the corresponding output will be u bar v bar plus vw bar plus u into w. So like that the expression will come. So in this way we are simplifying the Boolean logic using K-map. So next one is the sum of product term. So what is the mean by sum of product?
Adding all the products in the circuit.
X by plus.
Yeah.
Y plus XZ.
Yeah.
Yeah. So actually you are having two types of terms are there. One is a sum of product, and there's a product of sum. And the sum of product, which you already said, the adding the product of products of all the terms. So here you are having x bar y bar z bar, and x bar y z bar, and x y z bar. So this is the one form of sum of product. So what is the advantage?
Advantage is like easy to compute.
Yeah. Then
And like getting like shorter equation or like expression.
So one is computation is easy. Then another one is the level of logic we are considering in CMOS logic. It is easy to generate the structure for the layout. So that's why we are normally preferring the sum of product terms. Yeah. So next one is product of sum. So product of sum in the sense in sum of product what we are considering means instead of we are considering all the outputs as one, so we are grouping that values. But in product of sum we are considering the zeros. So, and we are grouping those zeros, and in that value has to be comes at the output.
Yeah.
So that's a difference between sum of product and product of sum. So actually, if we compute the sum of product, then the complement term is the product of sum. So we are able to
Okay.
generate because both are in dual in nature. So if we compute the either sum of product or product of sum, from that if we are taking the complement, then we are getting the alternate form.
Okay.
Then next one is the don't care condition. So what are the don't care conditions?
So we do either 0 or 1 can sit in the box.
Yeah. That means if the output we don't know means we normally taking that value as either D or X. So that the variable, if the grouping is possible, then we are considering that as a 1, either case, or maybe it may be 0 if there is no grouping is possible. So in that case,
Yeah.
yeah, in that case, if you are seeing this truth table, sorry, K map, here you are having one variables D, and here is also D, and here is also D, and remaining empty boxes are zeros. So if we consider this K map, here we are taking this D values as 1 because there's a grouping is possible here. So we are considering this D as 1. In that case, if we are taking this D variable alone, here there is no ones are adjacent here. So we are not considering this D. So this variable is taken as 0.
Okay.
So the don't care condition is actually applying for in two strategies. One is for reducing the low power strategy. If I'm applying any special techniques to reduce my power consumption, then I am considering that don't care conditions term, or else that value will be taken as either ones or zeros. Because if I'm considering directly that variables as ones or zero, it will consume more power in circuit CMOS implementations. So this is why we are using. Yeah. Pardon me.
No, you said if you consider even it as 0, the power consumption is more, right?
Yeah.
Okay.
Actually, if you are going in depth of your CMOS digital circuits, because which is consists of only NMOS and PMOS circuits now. So in that case,
Yeah.
we are applying some special techniques to reducing the power consumption. Because whenever we are considering the VLSI circuits, major objective of our VLSI circuits implementations are only the area reduction of area, power, and delay. So nowadays we are using only the mobile computing devices or mobile phone devices. So in that we are main objective after the timing criteria, we have to consider the power consumption. So the major probability to reduce the power consumption is the major concern of any design after the
Okay.
timing criteria. So in that we are using some state machine reduction techniques, then some encoding techniques. Then afterwards, one form of power consumption reduction is considering the don't care condition instead of either zeros or ones for initializing purposes.
Mm-hmm.
So that's why I'm saying. So
Okay.
so don't care conditions. If we are considering that value is 1, then only when it is when the grouping is possible. Otherwise, we are considering that D as 0. So next is a combination circuit. So combination circuit. Hello.
Yeah.
What is a combination circuit?
Combination of logic actually, like and or, like
Uh,
half adder and full.
yeah. Sequential circuits also the you are having the normal logic gates. Then what is the difference
Normal
between
logic.
combinational and sequential?
Sequential we have clock and like they have flip flops.
Flip flop. Okay.
Clock, they have clocks.
Uh,
Clock. It runs on a clock.
Actually, the main thing is the combination, the output which depends on the present input alone.
Yeah.
That means there is no feedback between your output and the input.
Oh.
Okay, so
Yeah.
a clock is a necessary thing in a sequential circuit. But in the case of if we are generally saying, what we are saying means the output which depends on the present input, then it is a combination circuit.
Yes.
In case of sequential circuit, the output depends on the present input
Previous.
and the past and the previous or past output. The next state output will depends on the
Current and previous.
and the past output and the previous output. So that's a sequential circuit. So there's always a feedback or memory element is present inside the sequential circuit. So for combination circuit, we know the main example is a adder circuit. So in that you are having half adder and full adder. So half adder in the sense, hello,
After the and NAND and NOR.
NAND and NOR, NAND and NOR,
And then not.
NAND and NOR.
and an XOR. So half adder,
Extra.
not NOR.
Yeah.
So actually, how we are computing that output means here you are having two outputs. So there's a carry, sum and carry. So here I am having two inputs x and y, 0, 0, 0, 1, 1, 0 and 1, 1. So in that carry is how the carry is generated means if I am adding this 0, 0, then the sum will be 0, and 0 plus 1, the output will be 1, and 1 plus 0, the output will be 1, and 1 plus 1, that output will be 10.
Yeah.
So the carry is here 1 and the remaining carry is 0. Only when both the inputs are 1, then the carry will be generated, or else then there is no carry will be generated, and the sum will be like that. So if I am considering the K map, so I have to put the K map means here 0, 0, 0, 1. So in that there is no grouping are possible because you are having only one single element, that is x into y. So C equal to x into y. And in the case of sum 0, 1, 1, 0, here there is no adjacent terms are there. Only the corner elements are 1. So we are not able to group these two elements. So the output will be x bar into y, x into y bar plus x bar into y. So x into y bar plus x bar y, we know that's a XOR gate. So x in x XOR y. So if I am draw the logic diagram, then you are having x into carry equal to x into y, and the sum will be x XOR y. So in the case of full adder, the same thing. Here 0, 0, 0 means 0, 0, then 0, 0, 1, carry 0, sum 1, 0, 1, 0, carry 0, sum 1, 0, 1, 1 means 1 plus 1, it's a 10, so carry 1, sum 0. Here 1 plus 0, 1, so sum is 1, carry 0, so 1 plus 1, 10, so carry 1, sum 0. Here also 1 plus 1, 10, so carry 1 and sum 0, 1 plus 1, 10, plus 1, 1, 1, that means 11. So carry is 1 and sum is 1.
Yeah.
So if I am considering the truth table, then if we are simplifying the expression through K map, you are getting carry equal to x XOR y XOR Cn minus 1, or xy plus x XOR y into Cn minus 1, C suffix n minus 1. So for the case of carry, for case of sum, which is not possible to group all the elements. So if we are simplifying the expression using Boolean algebra, we are getting the expression like that: x XOR y XOR Cn minus 1, or in terms of two, that means using two half orders, we are considering the expression like that. For a carry, this one will be the expression, and for sum x XOR y XOR Cn minus 1.
Yeah.
So in the case of simplification, if you are having any doubt means you can ask me, okay?
Yeah.
So if I am drawing the if I draw the logic diagram means I am getting the logic diagram like this. because you are having
Okay.
yeah 2 XOR gates in some expression. So here 1 and here 1, so x XOR y and Cn minus 1 into XOR into this term, that means x XOR y. So that will be actually our sum. And for carry, x into y plus x XOR y into Cn minus 1. So this is the term x XOR y into Cn minus 1. So you have to sum both this term and this one. So that is why you have to use the OR gate. So that actually which contains the Cn carry.
Okay.
And the other combination circuit will be multiplexer and the encoder, decoder, and parity checker, parity generator, and demultiplexer. So other elements which are consist of only the output, which depends only on the input, means that's a combination circuit. So here you are having a 4x1 multiplexer. So in that the multiplexer in the sense
Sorry.
so actually multiplexer is a the another name of multiplexer is a data selector.
Okay.
Data selector, actually through the selection line, out of 4 or 8 combinations, we are choosing any of the input to the output. So here here you are considering the 4x1 multiplexer. There are 2 selection lines.
Okay.
For 8x1 multiplexer, you are having 3 selection lines.
Yeah.
So
Depending on the number of binary.
Depending on the inputs, you are selecting any of the that means depending on the selection line, you are selecting any of the input to the output. So if it is
Yeah,
0 0, say
and converting it to binary, then you'll get the selecting line.
yeah. Here if it is 0 0, then I0 will be connected to the output y, and if it is 0 1, then I1 will be connected to y, and if it is 1 0, then I2 will be connected to y, and if it is 1 1, then the output will be I3 output will be connected to y. So
Okay.
so here if you are this is the internal logic of our multiplexer. In case of 2x1 multiplexer, you are having only one selection line and one output. For any of the multiplexer, you are having only one output. And for 4x1 multiplexer, here 2 power 2 combinations. That means based on the actually n is the number of selection line and 2 power n is the input.
Okay.
So here you are having 2 selection lines, so you are having 2 power 2, so 4 inputs. And in case of 8x1 multiplexer, you are having 3 selection
2 power
lines.
3.
So 2 power 3,
Yeah.
8 inputs. And if you are considering this logic here 0 0, so S0 bar and S1 bar, which is connected to the output of input of AND gate, and in that the I0 will be connected.
Yeah, and the whatever I value will come out.
And if it is 0 0, then I0 will be connected. For example, here if it is I0 value will be 0 means, then here 0 will be come, 0 will come, and if it is 1 means, then 1 will come, irrespective of this inputs I1, I2, and I3.
Yeah.
Okay, so that's why we are calling that multiplexer as a data selector.
Okay.
Then encoder. So octal to binary encoder.
Octal to binary.
Octal we know.
Converting like octal number to binary 0 number.
Converting
Octal
to binary, yeah, the binary encoding or binary conversion, both are same. So actually, octal we know 0 to you are having the value between 0 to 7. The next output will be
0 or 1. I mean zeros and ones.
that means for example if the value will be in octal form, the expression is how we are taking means 0 0 0, then up to 1 1 1, then the next value that means if 8 is coming means what we are doing means for 8 we are considering 0 0 1 0 0 0. because which is automatically reset to 0 because there is no 8 in octal number.
Okay.
So
Yeah, sir.
for by octal to binary encoder, what we are doing means we are just drawing the truth table. That means 0 to 7, and here 0 to 7 both are same logic. Then in encoder, encoding in the sense
Encoding means like creating and converting a new number.
Converting a new logic. So here usually what we are saying means in the encoder functionality, if you are having 2 power n input, you are having n output, n number of outputs. Okay. In the case of decoder, if consist of n input, then you are having 2 power n outputs. Yeah.
Vice versa.
Vice versa. So here you are having D1, D2, D3, D4, D5, D6, D7 because you are having the output will be in the form of input will be in the form of octal logic. So you are having 0, 0, 0 to 0, 0, 1, 1, 1. So 0 to 7 only we are having. And for binary logic, up to 15 if I am writing means 0, 0, 0, 0 to 1, 1, 1, 1. So if I am considering that octal to binary truth table by the simplification expression, you are having A0 equal to D0 plus D3 plus D6 plus D7, and A1 equal to D2 plus D3 plus D6 plus D7, and A2 equal to D4 plus D5 plus D6 plus D7. So like that the expression will come.
Okay.
So only thing, if we know the functionality, we just using the truth table to convert the input and output logic. Then afterwards, through the K-map simplification, we are getting reducing the expression. Then after drawing the logic diagram, means we are getting like that. So next one is the decoder. So decoder, I said, if it contains n number of inputs, then the output will becomes 2 power n. So encoding functionality where we are usually preferring means priority encoder. That means if I want to find the priority of any logic, then I am using the encoder circuit. Then for decoding,
To convert it again back to the original function.
Yeah, in the form of cryptography logic. So in that we are using only the decoder circuits. Then another one application is a address generator. If I using memory elements, so in that I have to choose which memory I have to write or read my content. So for that I am using the decoder circuit to select the particular memory array. So in that circuit we are using the decoder circuit. So decoder, if you are seeing the truth table, actually 0, 0 means only the output of D0 will be 0, and 0, 1 condition only the D1 will be 0, and 1, 0 condition the D2 will be 0, and 1, 1 condition D3 will be 0, and for remaining output will be all are 1. So actually the decoder circuit which is mainly used in the address selection in your normal memory elements. So that's why we are preferring the decoder for address selection, because you are having only one content is selected out of all the output. Okay. So what is the difference between demultiplexer and decoder?
Demultiplexer is like a
Multiplexer, you are having one output and 2 power n inputs.
Yeah, 2 power n.
Demultiplexer is 2 power n inputs and 2 power n outputs.
N input. No. Actually, only one input. Demultiplexer. In decoder only you are having N input.
Yes.
Okay. Actually, in
And what is
demultiplexer.
multiplexer? Sorry.
Pardon me.
The demultiplexer, one input and multiple outputs?
Yeah, only one input and multiple outputs. That's why the
Okay.
term of a demultiplexer is always called as a data distributor. So which consists of
Okay.
selection line in the same like a demultiplexer. So based on the selection, we are connecting that input to the particular output.
That's for the, in demultiplexer, you said you have only one input and you'll have several outputs, right?
Yeah.
So, how is that one input selected from the multiplexer, or it's like we priorly select that input?
Actually, if you're seeing the multiplexer diagram,
Yeah.
you just consider that inside. Actually, sorry. Actually, in demultiplexer, I'm not having the diagram here. So actually, what we are doing means the output here y is there now, so that will be coming on input side.
Okay.
The diagram will be like that.
Mm.
So this is one input, either I1, I2, or anyone. And if it is a 1x4 demultiplexer, then I am having two selection lines.
Yeah.
Yeah.
Two selection lines, and I am having four outputs.
Mm-hmm.
So likewise. So in that, actually what we are doing means the output is always connected through to the any of sorry, the input is always connected to any of the output. Only the selection line is changes. So for example, if it is 0 0, then the output this one will be connected to this one. Okay,
Okay.
and if it is
I
0
got it.
1, then it is connected to this one, and if it is 1 0, then this input is connected to here, and if it is 1 1, then this input is connected to here.
So you generally use that for changing the
Yeah, changing the input.
I mean, distribution of input.
Distribution of input. That's why it is called as
Okay.
a data distributor. But in the
Okay,
case of
got it.
multiplexer, that is a data selector, because any of the input has been selected to output through the selection.
Yeah.
Okay.
Mhm.
So so this is a so that's what a difference between your decoder and demultiplexer. So in decoder, what we are having means we are not having any selection line. But in the demultiplexer, you are having a selection line. So, and you are having n number of inputs here, and in demultiplexer, you are having only one input. So among that, you are selecting that input through the selection line. So that is the difference between your decoder and demultiplexer. So next one is a sequential circuit. So sequential circuit already said. So if there is a feedback is present, then the combination circuit which acts as a sequential circuit. That means actually the feedback which retaining the memory, that means which retaining the previous output. That's why which is called as a sequential circuit. So if you are considering this two NOT gates are connected cross coupled together, so the output, if you are considering here, if it is 1, then the output will be 0. That same output is coming on this one, and here
Yes.
1 is always connected to here. That means if I am considering this, the output will be actually in sequential circuit. Always we are considering the output alone first, without that means
Okay.
without considering the input. So here initially I am assuming here 0. So the alternative form here is a 1 because it is if we are taking this output is q and this one will be q bar.
Okay.
So here if we here this value is 0 means then it is 1 here. So that output will be coming on this side, this input side, and this output will be coming on this input side. So this value will be always the same thing. And if I am considering this one, then means instead of 0, if it is 1 means here 1 and here it is 0. So the value will be like that.
Okay.
So you are having 4 types of flip-flops are there. One is a RS or SR flip-flop, then
Yeah. J.
JK, then D,
JK
JK flip-flop, D, and T flip-flop.
Yeah.
So, so in that case, if you are considering RS and Q, and the output will be Q bar here, and this is a OR based or NOR based structure of SR flip-flop. So if the inputs are 0 0 means, then the next state Q of t plus 1 equal to Q of t. That means there is no change. And 0 1 means then it is a reset state. Then 1 0 means then it is a set state, and 1 1 means forbidden or metastability.
Okay.
So
It's
yeah.
If it's 1 1, the operation will be nothing, right? It's like a don't care condition kind of thing
Yeah.
for flip-flop.
Yeah. Actually, in SR flip-flop, there is a condition called as metastability.
Metastability.
Metastability. So actually, what we are considering means, if I am considering that this value will be 1,
Okay.
that both S R and S, these inputs are 1 1 I am considering, and in that case,
Yeah.
if I am considering the Q as 1 and Q bar as 0. So the output actually what will come here means, if I am considering this here the output is 0, then automatically here the output will be here the input will be 1, and here it is 0
Yeah.
we consider. So here 1 into 0. So 1 plus 0 equal to
1.
1. So the complement will be here
0.
0. And what we are actually initially what we are considered means, here we are considered as 1, and the output will here is 0. So here if the value is 0 and here the our input will be 1. So 1 plus 0 1. The whole bar is 1. So no. 1 plus 0 1 0 here is 0. And here 1 plus 1 1. So here is also 0. Did you understand?
Yeah.
I mean, like
Q and Q bar both
Actually,
are zero.
yeah.
Q and Q bar both are 0 if both the inputs are 1. Actually, what we want to consider means, here Q is 0, then it must be 1 in the Q bar side.
Yeah.
Or else,
But it's
means
0.
In that same case, if I am considering instead of 0 and 1, if I am choosing in Q1 and Q bar 0, then which is also the same output will come. That means both the output will becomes 0 0.
Yeah.
But in my case, what actually will come means, either if the input is that means if the output is 0, then Q bar must be in 1, and if it is 1, it must be in 0. But in 1 1 condition, there is no output like that. So that state is called as actually a metastability state or forbidden state.
Okay.
So the output which is not correctly at the Q and Q bar side. So which gate is faster, that gate output will comes at the Q.
Okay.
Okay. For example, if the Q if this gate is faster when compared to this one, then the output of R will come on Q and Q bar side.
Yeah.
Okay, so that is a metastability state or unstable
So
state we are calling.
yeah,
So
if it's in a continuous clock-like cycle, then we can't expect that stage, right?
yeah. That's why we are using, we are preferring the another three types of flip-flops instead of RS. That means the one condition will never occur in our circuit. Then only the output will correct for all the
Correct.
operations.
Yeah.
Okay, so if I am
Yeah.
considering, but the basic gates are formed only by the RS flip-flop. That means remaining
Okay.
all the flip-flops are formed only through this RS flip-flop. So if you are considering that SR flip-flop, so you are having two types of that means sequential circuits are there. One is a latches and another one is a flip-flops.
Okay.
So latches are
Level sensitive.
level sensitive and flip-flops are edge sensitive. So level sensitive in the sense,
Like they operate on a level, either 0 or 1.
instead of
Not
level
on
0,
the
level 1. Yeah. And in case of flip-flops, we are having a clock pulse. But the operations are almost same, but the output changes with respect to the edges, clock edges, independent of
Okay.
your inputs. So that's why we are preferring the flip-flop in your memory elements. So this is a clocked flip-flop, and if it is a positive edge triggered, then there is no bubble in, inside the clock. And
Okay.
if
Yeah.
it is a negative edge trigger, then there is a bubble. A bubble will be indicate that it is a negative edge triggered clock.
Okay.
Then you are having externally two inputs. That means preset and clear. So clear for resetting the entire flip flop, and preset means we are initializing any value for the intermediate operations.
Oh. Okay.
Okay, that's then another one is a D latch. So D latch we know in RS flip flop
delay.
you are having, yeah, RS flip flop you are having a metastability state. So we are terminating only by
Adding a delay to it.
one case is I have to delete these two values. So what I
Okay.
am doing means here I am just connecting one NOT gate. So if the input is yes is 0, then alternatively R will be 1, and if it is 1, alternatively it will be
Yes.
0. Okay,
Yeah.
that's what
You don't
yeah,
get the.
that's why you are having only two states. So
Yeah.
this is a normal RS flip flop. So in that we are in interconnecting these
The.
two terminals with the NOT gate.
Okay.
So if the input is 0, then the output will become 0, and if it is 1, then the output will become 1. So that's why it is called as a D latch or transparent latch. That means whatever the input we are given, that is coming at the output side. So next one is a, so latches we already said. So level triggered in the sense from the input level 0 or level 1, their output will change. So whenever the level will change, then the output changes will replicated. But in the case of HD card or clock pulses, irrespective of your input, only the clock changes, then only the output will come. Okay,
Yeah. Yeah.
so that's why we are considering the flip flops rather than the latches in a memory element. So, so next one is the JK flip flop. So JK flip flop, what we are considering means in the same thing. In the SR flip flop, actually the Q output will be coming to K AND gate, and the Q bar will be connected to this J1, J. So that in the 1-1 condition, actually there is a metastability state occur, but here there's a toggling state. And the Q of t plus 1 equal to 1 when q of t equal to 0 and q of t plus 1 equal to 0 when q of t equal to 1. So that's actually a toggling state.
Okay.
Actually here if you are seeing 0 0 means q of t,
Yeah.
Yeah.
0 1 0 1 0 1. So these three combinations are same for jk, but only thing we are removing that metastability state. So by that here we are connecting this output to this side and this output to this side.
Mm-hmm.
So for one condition the output will be in q of t bar, that means toggling state. So
Okay.
q of t equal to 0 means then q of t bar equal to 1, that's the actual output of q of t plus 1. And q of t equal to 1 then q of t plus 1 equal to 0. So for one condition the output will be q of t bar.
Okay.
So next one is a clock period. For any digital circuit we must know the clock period, because we are going to design a sequential circuit. If we want to perform the timing analysis we must know the operation of a clock, and the clock period must be usually consist of a delay time, then setup time and the hold time. So do you know the delay and setup time and hold time of a flip-flop?
Yep. Setup time is like the time before the clock pulse that like our input should be stable and hold would be out after the clock.
After
Like
the
for a
clock pulse arrives, the output must be stable to sample the output.
Yep.
And delay time?
Delay time, I don't know delay.
Is it the time taken by the circuit to
Reach
perform?
the out to give the output after giving the input. Is
Delay
that the
time
whole
is
time?
yeah, actually for delay time if you are considering means both flip-flop time period plus the addition of your logic combination
After
logic circuit. Yeah, after giving the clock pulse, how the combination
How much time it will take output?
the output of combination circuit, that means between the two flip-flops
Okay.
the time taken to sample the output between two flip-flops, that's actually your delay time. So for the clock period it must be the combination of delay time plus sample time and the setup time and the hold time. So the clock must be in, how we can calculate the setup time?
It should be like greater than clock period minus hold time minus the delay.
Yeah.
The equation that you have given, if you take the other two
Clock period
variables
equal
on
to td plus ts plus th.
Yeah.
Yeah. So actually if the clock period which is less than this period means actually what will happen means I will not get the correct output.
Okay.
Okay.
So the proper clock timing is necessary for working of the particular circuit. Yeah. So we know it's a combination circuit and which consists of a feedback that actually forms a memory element, then which is given to the combination circuit. So in that we are getting the output likewise. So next one is a state diagram. So state diagram means
Don't know exactly.
don't know. Okay, yeah, fine. So actually state diagram in the sense you are having a number of states which defines the input and the output. Actually, you are having two types of state machines are there. One is a Mealy machine and another one is a Moore machine. So in Mealy machine, the output which depends on the state and the input, then it is called as a Mealy machine. And in case of Moore, the output depends only on the state, not on input. So that is a
Okay.
Moore machine. So if you are considering that you are having four states, that is a 0 0, then 0 1 and 1 0 and 1 1. And in the case of 0, that means x is a input. So if it is 0, which is on the same state, and if it is 1, then it will changes to next state. So from 0 1, the same thing. If it is 0 for all the states, if it is 0, then the next state will be the same state. And if it is 1, it changes to the another state.
Yeah.
And here they are given for 2-bit counter. So here the current state will be 0 0. Actually we know counter means for a 2-bit counter the output will be 0 0 0 1 1 0 and 1 1, and it is automatically reset to 0 0. So you are having current state as 0 0. Then if 0, the next state will be 0 0, and 0 0, then if it is 1,
0 1.
it is 0 1.
Next.
Yeah.
Yeah.
So here the inputs are based on the input, the state will change.
Okay.
Okay.
And we are not externally, that means explicitly specify the output here. So that it means it is a Moore machine, because inside the state we are defining the output. That means 0 0 means which defines the state as well as the output.
Yeah.
Okay. So that's why it is called as a Moore machine. So if I am using the JK flip flop, then the output will be like that: JA, KA, and JB, KB. Because you are having two flip flops. Because you are having two states: 0 0, 0 1, 1 0, 1 1. So two variables. So you have to consider two flip flops here. So here, do you know the excitation table?
Which one?
Excitation table. Excitation table.
No.
No. Okay. So excitation table in the sense, truth table, you know. Normally, truth table in the sense, based on the input, the output, then what is the output will come. So that's actually a truth table. That and in case of excitation table, from the state or output, we are defining the input.
Okay.
That is called as an excitation table. So this is a state table. That means you are having current state, input, and next state. So excitation table. This is the input we are defining from the state table. So here, if you are considering 0 0 0 means then 0D. So actually, 0 D means don't care.
Oh yeah, why will get don't care here?
Actually, if you are considering the JK flip flop, what is the output of a normal truth table for JK flip flop?
JK flip flop
0 0 0 0 1 1 1 0 1.
0 0 no change. That means Q of T. And 0 0 1
1
0 1
1 0 1
1 0 1 and 1 1 Q of T bar.
Q bar T. Kaadu. No.
Q bar T.
Yeah, right. Q bar T. Yeah. Complement of the first thing.
Yeah. So this is
Q of T. Yeah.
Q of T, and this is 0, and this is 1,
0,
and this is Q bar of T.
Yeah.
So this is a truth table for JK flip flop. Actually, if you are taking this value here, I have to consider the input and the state.
Okay.
So if it is 0, then the state will be 0, input is 0, and the next state will be 0.
Yeah.
So 0, 0.
0.
So this is for state. And the next state equation is 0. Current state is also 0.
0.
Okay, well, that means
Yeah.
Q of T equal to 0. That means Q of T plus 1 equal to 0, and this is Q of T equal to 0.
Yeah.
So when will the output will become 0? Here. There is no change. For one condition, this is 0. Sorry.
Yeah, and for the next
0, comma 0 is one condition. Then when will my output is 0, 0 and 1. 0, comma 1. Okay, well. So if you are considering, so first one is a J input and next one is a K input. So here both are 0. So here it is J is 0 and here 0 and 1. That means complementary. So that's why it is called as a X. That means don't care on D. So one input is 0 and one input is D. So if you are considering JA and D. Okay. So like you have to define. You have to compare the current state and the next state. By that we are defining our input. So that's why the excitation table.
Okay.
So here both are 0. So the JA will be 0 and KA is also a D. And here if you are considering 0, 0, okay, 0, no problem. 0, 0, 0, 1. And if you are considering the fourth state, here 0 and here it is 1. So 0, 1 means?
0.
0, 1 means one condition is a 1, 0.
Yeah.
Comma 0. And another one condition is a actually here it is 0 and it is 1. That means toggling. So Q of T bar. So 1, 1 condition. 1 comma 1. So 1 and this is D. So JA D. Yeah. JA will be 1 and KA will be D. Or you can use X. In some books they are preferring X and in some of the books they are preferring D. So for your convenience you may use any of the variables, either D or X. Hello?
Yeah. Hello.
Yeah. So do you understand how we are defining the excitation table for JK flip flop?
We got it.
Similar way, if any of the in any of the questions, if they are asking for different flip flops, you have to use the truth table for particular flip flop, and you have to generate the excitation table for the flip flop, and you have to draw the diagram like that. Okay, va?
Okay.
So afterwards, if I am considering the K map for the particular inputs, so first of all, if I am taking for JA, then the K map is like that. So 1 DD is my inputs, and for 0 0 0, I just keep it as blank. So if I am grouping only these two variables or groupings are possible. So the output will be B into X.
Yeah.
And for KA it is B into X and KB equal to X and KB equal to X. So you are having two flip-flops because you are having JA KA and JB KB. So the output of this one will be A and this one will be B. Yeah, first one is like JA equal to B into X. So B into X in the sense, so this is JA and this is KA. So the output of second flip-flop that is actually B. So B into and the input is X. So you have to add together these two inputs. Then you have to given to the input of JA.
J.
And K is also the same. So you're just interconnecting both the inputs. So JA and K are equal to B into X and JB equal to X. So you just connect the input directly to the X and KB is also X. So you have to interconnecting both the values. The
Okay.
output Q is equal to A and Q is equal to B here. And this is a clocked sequential synchronous circuit. So you have to use the common clock for all the flip-flops.
Okay.
If it is asynchronous circuit, you have to use only clock pulse to the first flip-flop, or we are not able to use any of the flip-flops using clocks.
Clock. Okay.
Yeah, that's why it is a synchronous circuit. And next one is a shift registers. So shift register, you know, actually what are the input I will give, that input will be shifted to the output side.
Yeah.
Based on the clock we are applying. So here you are having a clock pulse and you are having D flip flop. So what is the functionality of a D flip flop?
Delay.
Delay means what are the input we are given, the same input will comes at the output side. So here all the inputs are connected in parallel. So here if I'm giving 0 1 1 1 here, so if I toggle the clock, then automatically the output is 0 1 1 1. For all the sequential circuits we are using the D flip flop alone. Sorry, for the shift registers.
Okay.
Okay, va. So here which is a shift right. So here if I am giving 1 0 0 in the first clock pulse 1 0 0 0. So initially if I am giving 1000 as input here, the first 0 will be shifted here for a first clock pulse, and the next clock pulse this 0 will be shifted here, and the next 0 from here will comes on this side. Okay, for the third clock pulse the 0 will come on this side, and the fourth clock pulse that 0 will come on this side. That means after the 4 clock pulses the 0 will be shifted here. So each element will consist of 0 and here 0 and here 0 and here it is 1, because my input is 1 0 0 0.
Yeah.
Okay, so only after the 4 clock pulses only we are getting the exact output. So before that the output of this flip flop will be unknown or in a reset state.
Okay.
Okay, so next one is a bidirectional shift register. So bidirectional in the sense, actually based on the selection line we are getting the output. So whatever the input we are here, for example here 0 0, here it is a 4 cross 1 multiplexer. So 0 0 0 1 1 0 1 1, 4 conditions are there, and all the selection lines are interconnected together. So for 2 selection lines you are having 4 inputs for a multiplexer. So one is a serial in of right shift and another one is a left shift, then parallel load, and another one is a serial in, serial out, in both are in right and left shift.
Okay.
Then third one is a parallel load. So that means what is the input I am giving, that output will comes on this side parallelly. And fourth state is a reset state. That means no change. The same output will retrieve on the output. So here 0 0 means here the input is connected here. So the output of this multiplexer is connected to this D flip flop. Then the A naught is connected to this one. That means this output is connected to this one, and this output is connected to this one, and this output is connected to this one, and this output is connected to this one.
Yeah.
Okay, well, or this output is connected to this variable. That means this multiplexer, and this one is connected to this multiplexer, and this output is connected to this multiplexer, and this one is connected to the output side. So actually, if I'm giving input on I0 side, then if the 0 0, if in the case of 0 0, then automatically that value will be shifted on right side. That means right shift is performing based on the clock pulse we are given. And if it is input is given at this side, then it is left shifted for 1 0 condition.
Okay.
For 1 1 condition, we are parallelly given to the inputs to all these 4 flip flops. So likewise, the operation will perform. And for sequential circuit, the one is a shift register, the next one is a counter. A counter, there are 2 types of counters are there. One is a synchronous counter and another one is a asynchronous counter.
Yeah.
For asynchronous counter, the example is a ripple counter, a ripple carry counter. So in synchronous counter, what we are doing means we are just applying the clock pulse. So here, if you are seeing, this is a synchronous counter because the clock pulse is common for all the flip flops, and
Okay.
this is a counter enable, and the J and K flip flops are interconnected. That means the J and K terminals are interconnected, and which is connected to a terminal called as a counter enable. Actually, we know for 1 1 condition, JK flip flop is toggling. Okay, va?
Yeah.
So if both the inputs are connected, so there is only 2 cases are possible. Either it may be in 1 or it is 0. So in case of 0, there is no change. That means what is the previous output, that same output will retain on this side. So here if it is 1, then the output will be automatically toggled. So if it is 1 here, then the output will here as initially all the flip flops are in reset condition. So if it is reset condition, if it is the counter enable is 1, then the output will become 1. So automatically it will toggle. So 0 1 0 1 continuously the output will comes like that. So automatically from that, if it is 1, then the output of this gate is also 1 because both the inputs are 1, because counter enable here it is 1, so which is in a toggling state, so which automatically generates like a clock pulse.
Okay.
So if here we are generating like a clock pulse, means automatically the output of this case will be 0 0 0 1 0 1 0 1 0 1. So it is continuously toggling here, and that output will be applying on this JK side. So here also
it will toggle again.
Toggle again. Toggle means how it is toggled.
1 0 state.
1 0 state. That means here 0 0 1 1. Then 0 0 1 1. So likewise for the final flip flop you are having 0 0 0 0 0 0 0 0, then 1 1 1 1 1. Likewise.
Yeah.
Okay, wow. That means number of delay has been increased here for next continuous flip flops conditions. Okay, wow.
Okay.
Here it is 0 1 0 1 0 1, and here 0 0 1 1, and here 0 0 0 0 1 1 1 1, then here 8 zeros and 8 ones. Okay, wow. Because after toggling, that means here all the flip flops are connected in toggle condition. So this AND gate will act like a clock pulse. So the automatically delay will be introduced on every JK flip flop. so which respond like a normal 4-bit counter.
Okay.
And next one is the memory element. Memory element, do you know?
Like
RAM.
Yeah, RAM, ROM. So what is the difference between RAM and ROM?
Read like the ROM is only used like stored memory, like one-time access.
Only when the power is on.
Power is on. The random is like you can alter the address. Like
Yeah.
you can store and
Mm.
write and read the address.
Yeah, fine, correct. So random access memory in the sense read and write memory.
Okay.
yeah.
Yeah. In ROM, it's a read only memory.
Only memory. Yeah.
So for in your systems, all the instructions which are stored in a, that means operating instructions, operating system instructions are stored in your ROM or RAM.
I mean, BIOS is stored in ROM and system instructions are stored in RAM.
Yeah, yes, correct. So that means whenever we are booting the system, actually that
Predefined instructions, ROM.
yeah, instructions which are already defined in the RAM. That's why we are booting the system. Then the instruction will execute whether we are having a operating system or not. If operating system is present, then the instructions of operating system which will be stored in our RAM memory, and the software usages which is also stored in the RAM.
Yeah.
Yeah. So in random access memory, you are having two types of RAM. So that DRAM and SRAM, and in ROM you are having EROM, EEROM, EEPROM, then
EEPROM.
PROM. So electrically erasable read-only memory, then
Programmable read-only.
Programmable read-only memory.
Read-only.
Electrically programmable read-only memory. So these kind of ROMs are there, and we are normally using the EEPROM or PROM in our normal circuits, digital circuits. And
EEPROM is
electrically erasable. EEPROM is a electrically erasable programmable read-only memory.
Yeah. Okay.
EEPROM is a electrically programmable read-only memory.
In systems, we'll be using EEPROM, right?
Yeah.
Or we can erase.
Yeah. In systems, we are using EEPROM.
Yeah, we can't be using EEPROM.
Yeah. Actually, in systems, we are using PROM only. Programmable read-only memory. Yeah. In the case of electrically erasable read-only memory, what we are doing means through electric pulses, we are removing the content of a content inside the memory element. And in EEPROM, actually you are having a portion to erase a content which is closed with a glass, that packaging. Okay. So through UV rays, if you are passing through that glasses, means it will automatically erase the content. But the problem using EEPROM is whenever I am exposing that UV light, automatically it will erase the entire content of my chip.
Yeah, it's kind of like the rewritable CDs, right?
We may say, but that actually a rewritable CD, which is like of which is similar to the EEPROM.
Okay.
EEPROM, actually EEPROM is a IC.
Yeah.
Okay. So in that we are having a packaging, and if you are exposing that UV rays in that portion, then automatically it will erase the content. And in real time, we are not using inside the computers or any of our computing peripherals. For large memory requirements, and if you want to delete the entire content of complete memory, then only we are preferring that EEPROM.
Like for servers and stuff, or
Similar to that, I will say actually I forgot where we are using that EEPROM.
that's fine.
I will refer and tell you on tomorrow.
Okay,
I was not able to recall that term.
that's fine.
So next one, so we know for read-only memory, you are already the content is already present in that memory location. So through the read or write pulses, we are retrieving the content from RAM. But in the case of ROM, we are using only read pulse.
Okay.
Because the already that means the element is already present in the memory, so we are only reading that element inside the memory, so we are not using the write pulse inside ROM. But in the case of RAM, we are using both read and write.
Yeah.
And next we have to choose the memory location in which portion I have to read or write the element. So in that I have used the address line. I already said in the decoder circuit, for address selection we are using the decoder.
Yeah. Order selector.
Yeah. So 1 KB means you are having 1024 bits.
Bits. Yeah.
So 1 MB of memory space means you are having
1 MB means
1000 into 1000 bytes.
Yeah.
1000 into 1000 kilobits.
24.
Yeah.
Usually we are on 1024 is actually actual memory, but for approximation we are saying always 1 KB or 2 KB, that almost similar to 1000.
Okay.
Yeah.
Okay.
Okay. So for you are having in your read-only memory, the address selection will be like that. So 0000001 010 011 100 101 110 111, and the output will be like that. X naught equal to 1, and the remaining content will be 000 and 001 1. X naught is 1 and X1 is also 1, and remaining values will be 0. So likewise we are retrieving the content. And you are having M cross and ROM. So M equal to 2 power K. Hello.
Okay. Yeah.
So that means you are having K address input lines
Okay.
N data outputs. So for example, if I am having 512 memory space,
Okay.
and M equal to 2 power K. So 32 cross 8 means
Yeah.
I'm having 32 number of memory elements, and the size will be 8.
8.
Yeah, that means 8-bit wide.
2 power 8.
Yeah.
Can you explain me one more time?
Yeah. Actually, if you're having 32 cross 8 memory locations inside, 32 is the number of memory elements inside that. That means one array which consists of that means 32 memory arrays are there, and 8 is a 8-bit wide data. Okay.
It's an 8-bit wired data, and there are 32 number of memory allocations.
Pardon me?
There's a 8-bit lines.
No.
Right? 8
address lines.
8 address lines and 32-bit of memory allocations.
allocations, 32 bits of memory allocations.
Yeah, which provides us 512 MB of.
Not 512 MB of, just I am saying the example.
Okay.
32 into 8, so that memory element is there. 32 cross 8 is the total memory size, memory capacity.
Okay.
Okay, well.
Yeah.
32 into 8 in the sense, 256.
Yeah.
Yeah.
That, 256, yes.
Yeah.
Okay. So this is the actual capacity of the memory. So next one is a ROM. So we know there's a different types of ROMs are there. One is normal PROM, EPROM, EEPROM. So
Yeah.
read-only memory. What we are doing is for mass production we are using ROM only, and we are just predefined our element inside the memory, and afterwards, after the production, we are not able to change that.
Like toys and other things, right?
In that case, we are not using RAM. Actually, we are just generating. That means we are writing our program inside that memory, and based on that content, it will automatically program.
Yeah.
And in the case of PROM, actually it is a programmable read-only memory, which is not changeable after fabrication, but it is very much costlier than compared to our normal erasable PROM. But in that case, if your production is more, then the cost is less.
Okay.
And we are using the that means inside the PLD we are considering the PROM.
I'm sorry, I couldn't hear the last.
In PLDs.
PLDs.
Yeah. One form of PLD is PROM.
Okay.
The next one is a PEPROM. In erasable PROM, what we are actually doing means through passing the UV light, we are erasing the content.
Yeah.
And afterwards, if you want to use the, that means if you want to program means we are easily program that IC.
Yeah, it used to be in phones, right? Actually, I mean,
Yeah.
like.
Yeah. Because inside the mobile phones, we are having EEPROM like that.
Yeah.
Then, so integrated circuit classification we already saw in the previous class.
Yeah.
And then the technology we are seeing means we are having 4 types of technologies are classified. One is a transistor logic, then emitter coupled logic, then metal oxide semiconductor, then CMOS, complementary metal oxide semiconductor. So the transistor logic we are using a bipolar transistors. So these transistors are used in the previous small scale devices.
Okay.
In the emitter coupled logic, then after the transistor implementations, using emitter coupled logic, we are using that means fabricating the ICs in the form of ECL logic. Then after the fabrication of metal oxide semiconductor, we are having CMOS devices. That means CMOS devices which consist of both NMOS and PMOS devices. So the main advantage of CMOS devices is low power consumption.
Low power.
Yeah. So that's why we are preferring that low power devices which consist of only CMOS devices. Then yeah.
The emitter coupled logic, is it like the transconductance amplifiers and the other stuff, or is it something different?
Which is also similar to that. Actually, in the emitter coupled logic, we are having a bipolar transistor and a resistor are connected together.
Okay.
So that's what it's a emitter coupled logic. And in TTL logic, you are having a transistor. That means you are only having bipolar transistor. But in
Yeah,
ECL
I mean,
logic,
you'll in the TTL you'll just be like having a transistor match with other transistor like current mirrors and stuff.
There's a lot of criteria are there. But real time, that means in current era, we are not using that TTL and ECL logics.
Yeah.
Because current implementation is only of CMOS logic. Because in the discrete components, that means small scale, medium scale integration devices, there only they are using the TTL and ECL logic. But nowadays, all the devices are in ICs. So
Yeah.
the CMOS devices are preferable one now.
Yes.
So
The size and
yeah.
power consumption was.
The power consumption is very much low, and the packaging density is also very much high.
Yeah.
And already we know now it is almost the research is going for 7 nanometer transistor size. So for CMOS
Yeah,
devices,
1,000.
more than 1 lakh transistors are million transistors are now they are able to fabricate in a single chip. Now they termed as ultra large scale integration.
Yeah. And the Microsoft is going under this research, right?
Yeah, Microsoft, Intel.
Yeah.
Intel and Qualcomm. So the major EDA vendors, they are having the research in that.
I mean, I have this one, but it's not related to the subject yet. The Dell has implemented the neuromorphic computing where they use like
Used inside?
like the Dell
neuromorphic
they
computing.
use
Okay, just complete.
Yeah, they use like the transistor logic, the basic transistor logic, non-Neumann architecture, and they started to build the neuromorphic computer. So, is it gonna change anything, or is it gonna be the same thing?
That means in the technology point of view you are asking, or in the CMOS or TTL logic you are asking?
In the technological point of view, not the CMOS or TT.
Okay. Actually, in the technological point of view, actually, in the neuromorphical, in the sense, based on our human brain, they are generating the number of neurons. Actually, there is a mixed signal design because they are interconnecting both analog and digital components. Okay, to design the memory function.
And they were also able to implement it in the processor point of view, right? They brought this called.
Yes.
Yeah, so that one, if that comes into the picture, then that CMOS will not be a
actually
thing undergoing.
What they are doing is the neuromorphic computing, the complete digital component fabrication is not possible.
Yeah. Not yet.
Yeah, actually already they are having the technology.
Okay.
By CMOS technology, what they are actually doing is they are fabricating both the CMOS and bipolar transistor in the same IC.
Okay.
Because they are having some criteria or some characteristics, and for bipolar it is having some characteristics. So if I want to use both the devices in a single element, then I am using the BiCMOS technology. Now all the devices are in mixed signal form because we want to process both digital and analog signals in a parallel order.
Yeah.
Okay.
For the yeah.
So the neuromorphic computing, actually we are having both analog signal and digital signals. Actually, some form of storage we are using the digital capacity. Okay, but in the case of analog, it is not possible. So for complete processing and sensing, they are using analog form in the bipolar transistors, and for digital storage, they are using CMOS devices.
Okay.
So they so that means they are combining both techniques.
Yeah.
And I mean, nowadays we are not purely using the digital circuits alone. We are using the mixed signal devices only. Whatever whatever circuits if we are considering or taking, we are using both analog and digital.
Okay.
So that's all about your basic digital circuits. So if you know thorough in that digital, then only it is easy to program a Verilog. Because without knowing the functionality of our hardware, we are complicated to program the functionality in Verilog.
Yeah.
So that's why I took all the basics of digital. So you just go through that, and if you're having any doubts, you can ask me in digital and Verilog.
Okay.
Your good name, please. Sorry, I forgot the name.
Actually, my name is Sharad.
Sure.
No, my name is Bhagirath.
Ethan.
Bhagirath.
Actually, we are like 4 people, right? So what we did is we bought the computer to the hall and we connected it to a TV and we are watching it in the TV.
Okay, fine. Okay.
Yeah, we're all sitting together and listening to the lecture though.
Okay. Then it is easy to interact with all of you. And if you have any doubt, means you can. That means you are group. You just discuss with one another, and if you have any doubt, means you just ask me. Okay.
Sure.
And next, so if you that means if you implement that means install that software, Xilinx ISE.
Yeah, we did.
Okay.
It's coming in
Actually, we got a problem with that. What we did was we actually downloaded the whole package.
Yeah, that's what I actually needed.
Yeah, so it's giving a virtual machine to us.
Virtual machine.
Yeah.
I mean, it's opening in.
Opening. No, actually, it's like a disk or wrap.
No, it's giving a separate. It's like a separate virtual machine which is running on Linux.
Linux, yeah.
Yeah.
No. Actually, you are having a package that instead of a complete ISE tool.
Yeah,
Yes.
ISE tool. Yeah.
ISC Virtual Appliances tool.
No. That means you are.
Can you send us the link
Yeah, of course, I will
to
send.
download that? Yeah.
But even I feel this is comfortable, right? I mean, like we'll have a separate memory for this one.
No, actually, which is actually implemented in our normal Windows system.
Okay.
Package is almost 14 GB after installation.
Okay.
The software package is 7 to 8 GBs, which hold the complete software. After installation, it will occupy 14 GB.
Yeah, somewhere around there. Like for us, it was when we downloaded it was 6.39.
Yes.
It was a RAR file, and now it's occupying like 13 GB of the disk space and 3 GB of the RAM.
Which is not a virtual machine. It is just you are having like icon is there. If you are that means it automatically installed there.
Can you send us a link where we can download this the software?
Okay, then I will send the link.
Okay, that's cool.
I'll send you my email address. Can you send to that?
Actually, as per our company policy, we are not able to. That means we are not able to send any email conversations. So better I will
send me in this one.
go to meeting. Okay,
Okay.
In go to meeting chat location, I will send you the link. Hello? 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 So can you hear me?
Yeah.
So I will send you the link on tomorrow morning session,
Okay.
and you can download it from there. Okay, va? And
Okay.
we will continue on the next class. Thank you very much. Thank you.
Thank you.
Thank you.